Okay, so last time we see the transport equation that comes from the conservation law. So we have these three terms. Okay, so next is the continuation of the previous model. Again, the transport equation, but this is the simple transport equation. Okay, so this is the previous model that we see from the conservation law. Okay, mentioned here, it can be simplified if we have certain specific assumption for Q and F, right? Because as we can see here from this equation, there are too many variables. We have the independent variable x and t, but the dependent variable we have rho the density, q the flux, and we have f1, okay, unknown function. So in terms of solving, if we have many variables, it will be difficult. Okay, so we can simplify so that to be depends on the method that we going to use. But for this course, we will use for the first part here, we will use the characteristic equation. So we will reduce the equation to be in terms of one dependent variable only. So that's why we need to simplify to have certain assumption for term Q and F. Okay, so in this case, we assume we have the assumption for Q in relation with rho, and F1 also if we have the assumption for it, especially if it is in terms of rho, in terms of variable x and t. Okay, sorry, not rho, in terms of x and t. Then this equation can be solved using the method characteristic equation. Okay, so now let us consider this assumption. The flux of cars increases linearly with the density of cars. Okay, so as we can see here, we assume that the flux Q, here flux is Q, it increase linearly with the density of cars. Okay, so we try to relate with the density rho. Density is rho. Okay, and flux is Q. So means later the term Q can be written as the rho terms. So the dependent variable here will be reduced into one dependent variable only. What would the original model become? Okay, so the answer here is this will be the model after we use this assumption. Del rho del t plus k del rho del x equal to F1. Okay, so for the assumption, usually in real, the assumption should be logical and so on. Okay, so in this case, okay, the flux increase linearly. The proof in the next page, there is a proof for this. So we say that flux increase linearly with the density of cars. Okay, I write in short form. Okay, so density is rho. Okay, so we have to understand the term linear increasing means here Q is actually equal to K rho, where K is any constant. Okay, K is constant. Or you can use any constant, C, and so on. Okay, so now if we substitute into the equation, we have the first term remains del rho del t, and then we have the second term plus plus del q del x, the original one. So we have del x, q we replace with this term, okay, from this assumption. So we have, this is rho, okay, k rho minus f1 equal to 0. Okay, so that's why we have the answer in the previous page is del rho del t plus k. K is constant, so means we can bring it outside of the derivative here. So we have k del rho del x. Okay, F1 here, if we refer back to our previous notes, F here consists of x or t. It may consist of x, it may consist of t, or both. It can be constant as well. So we can bring it to the right hand side like this. So now this is the model simple transport equation. I named it here when we consider the assumption that the flux increase linearly with the density.